So once we have learned the envelope theorem, it turns out it has a lot of application in different disciplines. But our focus in this course will be application in economics. So we'll discuss a special case. That is, we're going to interpret Lagrange multiplier as so-called shadow price in economics. And then it's basically what shadow price? Shadow price is really a special case of, so it's a special case of the envelope theorem, when only the constant term of the constraints are parameters. Okay? So shadow price is really a concept that arises when you use envelope theorem in a special scenario. Let us look at the theorem. The setup is the following. As usual, we have an objective function to optimize, okay? As usual, we have an objective function. But this time, the objective function has no parameter. Where do I have the parameters? The parameters comes in when I look at the constraint equation. And moreover, all the parameter a1 to ak, the parameters occurred as constant term on the right hand side of the constraints. Okay, so this is really a very special case, okay, of this previous setup. And then what does the envelope theorem tell us in this case? The envelope theorem tells us in this case is that this equality is true. So let me put a box here. That is, when you differentiate f, the maximum value function, with respect to one of the parameter, then you get the Lagrange multiplier. Okay, so this is very interesting. So the proof is actually very simple once you know the envelope theorem. So let, as usual, let L be the Lagrangian. In this case, the Lagrangian is given by the objective function minus, well, how many constraints do I have? I have 1, 2, 3, up to k constraints, so I need k Lagrange multiplier. So mu1 times the first bracket come from the first constraint, so I have h1 minus a1, and the minus mu2, and the h2 minus a2, and then minus so on until the last constraint, there's mu k, and the hk minus ak. Okay? Then I'm interested in differentiating the maximum value function with respect to my parameter. So for example, df mass dai by the envelope theorem, this equals to differentiating L, the Lagrangian, with respect to the parameter, and then evaluate it at your maximizer. Okay? But where is A1? Well, look at the Lagrangian. A1 is here. So when you differentiate A1, this becomes 1. So you get minus mu1 times minus 1, so you get mu1. And at the maximizer, what is the value of mu1 at the maximizer? The value of mu1 at the maximizer, well, look at the maximizer. What is mu1? Mu1 turns out equals to this guy, okay? So this equals to mu1 of A. And then we're done, okay? So done. But, well, of course, this is just about A1, but you probably imagine this proof does not depend on whether you're using A1 or A2 or A3 here. So you get an identical result for every single parameter. But what is so interesting about this? Okay, so let me put a line here. And let me put a remark. So, remark. remark. So suppose you want to consider the optimization problem, that is the production function. For example, I call it big F of xy, subject to a budget constraint. So budget constraint has the form P1x plus P2y equals to I. Okay? Because x and y are the input of your production, and each of them has a cost, okay, of price P1 and P2 respectively. And P1x plus P2y is the total cost of the production, and that equals to I. And I is the total budget of your production. But from what we find out above, okay, so by the envelope theorem and above, it implies when you differentiate the maximum production with respect to the total budget, then what do you get? You get the Lagrange multiplier. It's exactly the value of the Lagrange multiplier, because I is the constant term of your constraint equation. And then therefore, the Lagrange multiplier is referred as a shadow price, okay, so-called shadow price. In this case, because it is the rate of change of the maximum production, of the mass production, with respect to the total budget. Okay? So this is a very realistic question. So when you increase the total budget of your production, that means that you increase I, then you're interested in how does the maximum production will change accordingly. And it turns out, by envelope theorem, dF mass di equals to the value of the Lagrange multiplier. So Lagrange multiplier really governs how F mass change with respect to the total budget. And then for this reason, we refer to Lagrange multiplier as the shadow price, okay? Because it's really the rate of change of the maximum production with respect to the total budget. Let us look at an example. This is actually an example from the wet work of Calculus 3. But then at that time, without the knowledge of envelope theorem, this seems to be a very tricky question. But then with the help of the envelope theorem, it will explain very clearly why this question should be done in such a way. So let's have a look. Suppose the maximum value of the objective function subject to this constraint gxy equal to 2 to 0 is 7,100. And then at that time, you know that, well, you're given that the Lagrange multiplier involved is mu equal to 25. And then find an approximated value for the maximum of fxy subject to a tweak of constraint. So now constraint is changed. Instead of 2 to 0, it becomes 2 to 3. And you want to see how the maximum value of your optimization problem change accordingly. So we do the usual thing. We set up the parameterized version of the optimization problem. So we want to maximize the function fxy subject to gxy equals to a parameter a. For different a, you get a different maximum value. So we also let f mass that depends on a is the maximum value with parameter a. So for example, we're given F mass when A is 2020 equals to 4100. Moreover, we also know that the Lagrange multiplier mu will also given mu star, okay, when the parameter is 2020, the Lagrange multiplier is 25. Now we're asked to estimate the value of F mass, but this time the constraint constant becomes 223. How do we do that? The only way to do estimation in this course is by linearization. So by linearization, at what? At A equals to the initial parameter. The initial parameter is 220. Then we have F mass of 223 is approximately equal to F mass of 220 and then plus dF mass dA evaluated at A equal to 220 and then times, okay, now you plug in 223 already, 223 minus 220. Okay, so this is just linear approximation. But now we have this term here, the derivative. And the derivative can be done by using the envelope theorem. But because this time the constraint of the parameter happens in the constraint constant only. Therefore, in this case, the envelope theorem tell me that the derivative of F mass with respect to the parameter is really just the Lagrange multiplier. So, by the envelope theorem, or let me say simply the shadow price theorem, we know that this is really F mass of 220. This derivative is really given by just the Lagrange multiplier, but then at what? When A is 220. Sorry. Okay? So if you do not believe that, you can apply the envelope theorem to see it. But in this case, because we know that this is a simple case when the parameter happen on the right hand side of your constraint, so we can simply coach that this equals to the Lagrange multiplier. By now, we realize that both information here are different. So we can just plug that in. So using the given information, using what we're given, this is 7,100 plus 25 times 3, so it's 7175. So this is the approximated value for the new maximum of my optimization problem when the parameter now become 223. Okay?